Hello. This is Concrete Path. Today we are going for the concept of shear flow, shear center. We are going for the concept of shear center. Shear center. In the previous topic, we have learned that the shear flow variation in the cross section. So today's topic is that the shear center. We can also say that it's a unsymmetric loading. We call that topic as unsymmetric loading for thin-walled members. We already know what thin-walled members is. So we say that what is shear center and what's its concept to that if the loading is unsymmetric loading. Let's have the basic concepts. Let's revise the basic concepts. We had this beam. You applied a load of P, and you take any cross section, and the cross section looks like, let's say the cross section looks like a rectangle. And if the load passes along the principal axis, where the product of inertia is zero, that's principal axis. So for the rectangle, we have two principal axes. The two principal axes. One is this one PA1, and this is your principal axis 2. We can also call it as line of symmetry, or we can also call it as axis of symmetry, or we can also say that's plane of symmetry. Let's have some symmetry. We can say there's some symmetry about that axis. So if the load passes along one of those principal axes, that means the bending developed. There would be some bending. We can say that we have only bending in the member. There won't be any twisting. We can say no twisting of the members, no twisting of any fiber. So there is only bending possible. Now, similarly, if the section was, let's say section was I section. And we also have that two axes of symmetry. If the load passes one of the axes, so we say that there is only bending. Similarly, if you take any box section, let's say this is some box section, and we have two axes of symmetry, load passes one of the axes of symmetry, so we have that no bend, we have that only bending is possible, that no twisting. Now similarly, you have circle. If you have circular section, we have infinite number of principal axes. If load passes along any direction, we have only bending. We don't have twisting. We have only bending. So we have principal axis, infinite number of principal axes, similar to case of hydrostatic loading. Similar to case of hydrostatic stresses, where we have infinite number of principal planes. Similarly, we have principal axis, infinite number of principal axes. So there is only bending. Now after that, so this was the case. We can write the statement that this was the case for the members having two axes of symmetry. Now one more thing is that, now if the load was such that it was passing through the center of gravity, it was passing through the CG. Let's say the load was applied and it was passing through the CG. There is again no twisting. Only bending is there, no twisting. Similarly, you have the this I section, and there are two axes of symmetry. If the load passes along if the load passes through the CG, that center of gravity of that section, if the load passes from that, there is still no twisting. Similarly, you take any other section. Let's take box section. You have the CG. Let's apply the load at an angle of theta. We say that again there is no twisting. So we can write that statement. If the members have two axes of symmetry, and load passes along one principal axis, or it enters, and we can say it enters CG. If it goes along, or it's along the CG, there is no twisting of the section. No twisting would be there. Only bending is possible. So this is the first cases of that. Now next case is that let's say the section is not, let's say the section were the same. 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 But the thing is that the load passes at some eccentricity E. So the load passes at some eccentricity E. So for this case, we say there would be twisting plus bending. There is twisting plus bending. So load is not passing through the center of gravity, or we can say load is not passing through the principal plane, or we can say principal axis, or line of symmetry, or plane of symmetry, or axis of symmetry. Load is not passing from that, so we say there is twisting. Similarly, you have box section, load passes at some eccentricity P. I would say there is a possibility that, so there would be twisting plus bending. Similarly, you take any other, let's take any other section. Let's say I section. We have I section. We prefer I sections. Let's say this is the axis of symmetry, two principal axes, and load passes somewhere here. So there we can have twisting plus bending. So this is the next statement, that if we have two planes of symmetry, two axes of symmetry, and the load is not along principal axis, or it's not along the CG, then we can have twisting. Then we can have twisting plus bending. So this is the next case. This is the next case. Now we are taking that next cases of those sections. Now next section cases are next we can call it as B section cases. Now we have this section. Let's call it as angle section, or we can have channel section. We can have this channel section also in this fashion. So C section, channel section, and after that we can have T section. We can have T section. We can take T section. We can take these. Now the thing is that so for these, we say for the angle section we don't have any axis of symmetry. For the angle section we have no axis of symmetry. We don't have any axis of symmetry. We have principal axis, but we don't have axis of symmetry. So principal axis would be somewhere here at some value of 2ixy by ix minus iyy. There we can get the location somewhere, but we don't have axis of symmetry for the angle section. But for the other sections, we can say there is one axis of symmetry. For this one, we have this axis of symmetry, and for the T, we have this axis of symmetry. We can write one axis of symmetry. Now you apply load. Let's apply for the first case, that is along the axis of symmetry. Let's have for these cases. You apply load from the axis of symmetry. So you apply load on the axis of symmetry. Next one is that there is some center of gravity here, CG of the section. Some CG of the section would be somewhere here. Let's say there is some CG for this case also. So load is acting, for this case, load is acting along the CG. Along the CG. This is your CG. And for this case, if the load passes along the CG, we're saying what's going to happen. I would say that for the third case, load passes, P is along the principal axis. So I can say there is no twisting. There is bending, but there is no twisting. And for this case, we have axis of symmetry, and we can take first part that the load passes along the axis of symmetry. We have axis of symmetry, and along that line we have also that CG also. We have also CG also along that line. So load passes, P passes G, and you can remove that G. G is not important here. P passes that axis of symmetry. So we can say no twisting of the members. No twisting. There is no twisting. But for this case, load is not passing. We have one axis of symmetry. We have this axis of symmetry, but load is not passing. Load is perpendicular to that. We said P not passing axis of symmetry. That means P, there is twisting plus bending. So for this case, there is bending plus twisting. So this is critical condition for this one. So if the load passes CG, so you have the statement that we can write that statement later. Let's have this one now. So for this case, we have no axis of symmetry. If the load passes from the CG now, there's one possibility we can take, that if the load passes CG, and still we have twisting plus bending. We have still twisting plus bending. So how can you use this angle section then? If anywhere you apply load, you can have bending. Yeah, bending plus twisting. And if you do even apply along the CG also load, if you apply the load along the CG also, you would have twisting also. So for any other case, you have twisting, and if the load passes through the CG, you would have twisting plus bending. So how can you use this section now? This is the question, that how can you use this section then? There would be twisting of the members. If you are using it for bending, there is twisting also that gets developed. So how can you eradicate that bending, that twisting of that section? So that's one question mark here. So we can write the statement for this next case. We can write, if the two members, if the sections have no axis of symmetry, or they have one axis of symmetry, and P passes, I would say P passes, yeah, there might be confusion. If for the separate case, you write, if the sections have no axis of symmetry and P passes along the CG, there is bending plus twisting. Even the load passes through the CG, there is twisting plus bending for this those sections which have no axis of symmetry, and for those sections which have one axis of symmetry, and if I write, for no twisting to develop, the load should pass through the principal axis. This is your axis of symmetry, that load should pass axis of symmetry. That one, we have only one axis of symmetry. If the load passes along that axis of symmetry, there won't be twisting. So for this case, if you take this case, load is along the CG, P is along the CG, but principal axis is this one. It's not, load is not passing through the CG, so there is twisting plus bending. And for this case, if the load was passing along this axis, I would say there is only bending. And similarly for this section, if the load passes along this way, I would say there is only bending. But for this case, we have twisting plus bending, because load is not passing along the principal axis, but it passes through the CG. So for the other two cases, load is passing through the CG also, and it is passing through the principal axis also. So for the condition of that twisting, so we got one concept to that. For twisting to happen, for twisting to not happen, I would say load should pass, I would say must pass principal axis. Load should pass that principal axis. So we got this one. Then accordingly we can write now how can you, once we apply the question mark, now next topic is that how can you eradicate those that twisting of that section. Now for that, we have the concept of shear center. So shear center is the point. This is the point on the axis of symmetry. It's the point on the axis of symmetry. On the axis of symmetry, not on the, I can say not on the CG, but on the axis of symmetry. This is not the condition that it is on the CG. It can be there on the CG. There might be some chance that it is on the CG, but the condition is that it should be on the axis of symmetry. Such that transverse load, it passes along, if the transverse load, that is shear force, or we can say that transverse load of V or P passes along it, there is only twisting, there is only bending, and no twisting. So you got this statement that shear center is the point on the axis of symmetry. not on the CG, such that the transverse load, it passes along it. There is only bending of the member or section, and there is no twisting. So we call it as one more name. We call it as a flexural center. Flexural center. That means if the load passes along this, we have only flexure, that's bending. We have only bending, no twisting. We have no twisting. So actually the thing is that your twisting is because of twisting is because of that shear force. Because of that shear force, twisting is because of that shear force. We have that twisting, rho equals to tau by r into j. We have that because of the shear force, your twisting is there, torque is there, twisting. So if there is twisting because of shear force, we should say the load, your P or your shear force V, should pass at that point such that for the entire section, your shear force, the resultant of those shear forces, it should be equals to P. It should be equals to P. I would say one more definition, that that shear center is the point. It is the point on the axis of symmetry, such that your load passes. If the load passes along it, yeah, we can say it's the point on the axis of symmetry, which is the where the resultant of shear forces is there, where the resultant of shear forces passes through. So we say that if the point on the axis of symmetry is there where the resultant of the shear forces pass, we call that point as shear center. Now we have the rules. For locating the shear center. So first one is that rule number 1 for location of shear center. Where is the shear center located? Rule number 1. Let's say if we have two axes of symmetry, we say if the members have two axes of symmetry, then let's say we have two axes of symmetry. So this is your G, and we have this section, box section, we have two axes of symmetry. This is G. We have I section. We have two axes of symmetry. We can take S section also. We have two axes of symmetry. But the thing is that we should take equal dimensions of those flanges and webs. We have two axes of symmetry. This is your G. Let's say the load passes along the then we say that shear center would be at the location intersection of two axes of symmetry. So your shear center is also at that point where your CG is there. So your G and C overlap for these cases. C and G, they overlap for these cases. So the intersection of those two axes of symmetry in the section, we have that point, we call it as a shear center. So first rule is that if the members have two axes of symmetry, if the load passes through the intersection of those 2 points, those two axes, then there is only bending, no twisting, because that the point shear center is at that point of intersection. So for the next rule is that now if you have one axis of symmetry, only one axis of symmetry, let's call those sections as, let's say this is some T section, let's say this is some channel section C, and let's say this is also some channel section C. And is there any other thing? Let's take this case that we have one axis of symmetry, and we know that there is some shear force, there's some shear flow, and we say that the shear center is somewhere on their shear center is some point. If the load passes on that point, there is no bending. So it's at a location of, we call it as a E. It's at a distance of some value of E from some point O. So we say that if the load passes, if the shear center is at some eccentricity from some point O, such that it's the shear center itself is on the axis of symmetry. If you have one axis of symmetry, shear center is on axis of symmetry. Shear center is on axis of symmetry. Shear center is on axis of symmetry. But how can you balance that? How can you get this location? So we say that because by the definition of shear center, how can you get the location now where it's located? What is the value of E? What should be the value of E where it's located? We say that for the location of shear center, we say your shear center is such that it's the point where resultant shear stresses, where resultant shear forces pass. It's the point where resultant shear forces pass. So if you apply conservation of moments, if you say summation of moments at any point, you can get the that equate to 0. You can get the location of that shear center. Some distances, let's call them as some distances of d. So you can get the value of that particular location of E where the shear center would be. So second statement is that if you have one axis of symmetry, if the section have one axis of symmetry, the shear center is on that axis of symmetry, but not on the G, but not at the G, not at the location of G, but at some distance away from I can say from point O. So I would say it's not on the point G itself, but it's at some distance of some x from G, such that it's itself on the axis of symmetry. Then third one is that if you have two narrow sections, if you have two narrow intersecting sections, third one is that if you have two narrow intersecting sections, two narrow intersecting sections. Let's say you have T section. This was your one section, and next section is this one. So we have two sections. They are intersecting somewhere. Let's say their centroidal line is let's say for this one there is some centroidal line, and for this one there is some centroidal line. So the intersection of those two would give you shear center. But if you talk about the center of gravity, that is somewhere here. If you talk about the axis of symmetry, that is the axis of symmetry. We can say that if you have one axis of symmetry and the shear center would be at the location at some point at a distance of some distance x from center of gravity, but not necessarily on that G, but it would be at some location x from G, such that it's at the intersection of those two lines. So this is your S. Similarly, if you take that you have T, you have L section, also angle section. So I would say there is some center line of that member, and there is some center line of that member. So I would say this is your shear center location. This is your shear center location. And if you talk about its G, it would be somewhere here. Actually, for this one, you have some principal axis at some location, at some theta with respect to your one of the members, and then you got this your principal axis 1 and principal axis 2. Then this is your principal axis 2. It passes through the CG. Then there would be some point on that principal axis, such that the shear center would be at the intersection of those those narrow sections. So at the intersection of those two narrow sections, we can have the location of shear center. We can take that. Let's take this section as inclined. Let's say there is some section that's inclined section. So we would say that would be somewhere here. Your shear center would be somewhere here. Your center of gravity would be somewhere here. So your shear center is at the intersection of those two sections, narrow sections. Similarly, you can take T section in this way. I would say the intersection would be somewhere here, and you can apply the load along that point S shear center, and G would be somewhere here. And after that you can take an I section. Let's say this is your I section, but the two different flanges are not equal. Let's say this is some having some moment of inertia I, and this is some having moment of inertia I1 and I2, I1, I2. So the centroid would be somewhere here. Let's say the centroid is somewhere here. Let's say the centroid is G somewhere here. And I would say, what is the location of that shear center? We know that for if you have two axes of symmetry, let's say this is some thickness T, and it is equally that web is equally spaced. I would say we have one axis of symmetry, and along this axis of symmetry we can have shear center. We have only one axis of symmetry for I section, which is unsymmetric. It means unsymmetrical about next axis. It's symmetric about one axis, but that unsymmetric about next axis. So we have one that we have this axis of symmetry. Then after that, their shear center would be at that somewhere at that location, but it is closer to shear center is closer to the closer to the flange that's having more moment of inertia, to that flange. The shear center would be there, and it would be between your shear center would be between your G, and it would be and between the section and between the flange which having more I. So the shear center would be somewhere here. So your shear center would be somewhere here. Yes, between G and between the CG of that section, having more I. So you got this one. You got G more. You can write G more. So your shear center is between the center of gravity of the entire section and the CG of the section of the flange having more I, having more inertia, moment of inertia. So this is these are the rules for the location of shear center. Let's take the standard case of that channel section. Let's take the channel section. Let's take the standard case of channel section. Let's take the channel section. We had this channel section. Let's make it equally. Let's make the equal flanges. Let's say this is the flange 1 and flange 2. I would make it equally. Let's say that the width of the flange is B and the thickness of the flange is T. Similarly, the thickness of the web is also T. And I would say the total was D, and between those we have small d. Then finally we say that that thickness equals to d minus d by 2. And but we directly say there is some value of h, that is equals to, there is some value of h that equals to d plus t. Your h value equals to d plus t, d by 2 plus t by 2, that's d plus t. Or we can say h equals to capital D minus t. So we directly take that center to center distance that we represent as h, h. So we can finally make the diagram that looks like in this fashion. We have this diagram. Let's analyze this diagram. So we say that there would be some shear flow. Let's say that shear flow is in this direction. It depends on the loading. If you have sagging bending moment, we know that the top fiber is having compression and bottom tensile. Similarly, if you take any element A, then accordingly you can get the variation of that shear stresses. Then by the complementary shear stress that on the section there would be opposite direction. So it depends on the loadings. Let's say the shear flow is in this fashion. So we assume that the direction of shear flow is in this fashion. And for this section, we know that we have one axis of symmetry. Do you know we have one axis of symmetry? Do you know that we have one axis of symmetry? So this is your axis of symmetry. Now, if you apply load at some eccentricity, let's say this is some resultant load, or we can say this is the load P, or this is the load or shear force. This is the shear force you can apply on this cross section. If you apply this the shear force on this cross section at some eccentricity E, let's say this is some eccentricity E up to the point O, let's call it as O. So your eccentricity is from shear center to point O. So shear center to O. Then I would say because of this, because of the shear stresses in the flanges, and because of that, I would say there is some horizontal force. Now, if I make that some horizontal force based on the summation of forces, based on the summation of fx and based on the summation of fy, I can make some forces. Because there is some shear stress, that means there would be some shear force. And there is some shear flow, and we have some thickness, we can say there is some shear force. Let's make some shear force of h. If there's some shear force of h in this direction, and from the top side we can say by the equilibrium of forces there will be some shear force of h. There's some shear force of h. Can we say that there's some shear force of h? And you're applying a load of shear force v at some eccentricity e. So there should be some vertical load of vertical shear force of v in the section, in the web of the member. Can we say by the equilibrium of forces? Can you say that? Can we say that? Now we can solve this part now. We can analyze this part now. So we can analyze this part now. Now I would say this is your h/2 and this one is your h/2 up to the center point. I would say this is your h/2 up to the center point, that is equals to h/2. Center to center is your h/2. And if we apply that summation of moments about point O, we know that from the rule 2, this was your rule 2. For the rule 2, if you have one axis of symmetry, and shear centers would be at the location where it would be resultant of those shear forces, and if you apply summation of moments at any point, and you can get the value of location of shear center. Now we can say that let's apply the summation of forces at that point O. I can write that, I can calculate the shear forces, that summation of moments. I can write V into E. Let's write anti-clockwise negative. So minus VE, then plus clockwise of h into h/2. Similarly, one more h into h/2. Because of this h into h/2, this one h into h/2 plus v into 0 equals to 0. That means VE equals to h into h. VE equals to h into h. We got this equation. Now the thing is that you want to say what's the value of h. We know that V is the external shear force on that cross section. There is some shear force diagram. We know that there would be some shear force at that particular location of V, at that particular location of X. So there is some shear force. Okay, but what is the value of h? How can you get this value of h? We say that there's, because of the shear flow, there is some shear, there would be some shear force h along the horizontal. But how can you get the value of h? So from the shear flow, let's say there is some shear flow. How do you know the variation of the shear flow? Actually, what do you know about the shear flow variation? Do you know anything about the shear flow variation? I know one thing, that the shear flow varies from z goes to 0 to some value of b, from z goes to 0 to some value of b. So we have some linear variation of shear flow from 0 to q naught. And similarly, in this part of the I can say web, there will be some shear force of q. And similarly from this side, shear flow of q, then it would increase parabolically up to the maximum goes to neutral axis. So this is your shear flow in the web. So I would say the value of h we can calculate based on this calculation. Say we know that the shear force per unit length, equals to shear flow. So your h, we can say h per unit length. We know that the length here, we can say the length here is equals to value of b. If I write h by b, that would give me shear flow. Then I can say your h value equals to q times b. Your shear force h, horizontal shear force h, equals to q times b. Yeah, but the thing is that had it been constant value, but along the length, along the width, if you have this width b, along this width we say that your q is not constant. You can multiply this one. This is the area of the rectangle. This is the area of the rectangle. But we have a triangular variation of the shear flow. So we can do the average of that shear flow. We can write here q average. We can write q average here. Let's write the q average. We can write that your h equals to then 0 plus q naught divided by 2 into value of h into value of width b, because along the width b your shear flow is varying from 0 to some value of q naught. So we can write average of that. So we got a value of q naught b by 2, that equals to some shear force q, horizontal shear force h. Now how do you get the value of q naught? So q naught is the shear flow in the channel part. So if you take that channel section, let's write that this is the neutral axis, and you want to take what is the shear flow in this part, in the channel, in this channel part. We have area of b into t. How do you get the value of shear flow in the part, this one, in the flange part? There is some value of h, but how to get the value of shear flow? So I would say you go to some value of y, y equals to h by 2. You go to value of y equals to h by 2. Then after that, there is some point A. Then area above that point A, it would give you shear flow. In the flange. So the area above that point would be area above equals to b into t. And if you want to say what is the centroidal distance of that bt, that's at somewhere here. That's at a distance of, we know that total equals to h by 2 plus t by 2. Can we say that total of h by 2 plus t by 2? H by 2 is up to the center. Then after that we have thickness by 2. Can we say? So we are your value of h plus t by 2. So you got this value of ay bar equals to bt into h plus t by 2. So let's write that shear flow. We know that shear stress equals to shear flow by width. If you use that, if you write that shear flow equals to vq by it, vq by I, this is your shear flow. If you write that v into your value of q would be equals to b into t into h plus t divided by 2 and divided by I. So you got this value. You got this value of vbt h plus t by 2. Now how can you solve for the value of t? How can you solve for the value of t? Yeah. Oh, OMG. See the correction. See the mistake. Actually, the centroid is somewhere here. And that is itself the value of h by 2. Isn't it? The centroid is at the value of h by 2, because the value of h by 2 is at the center. So we are taking the area. It is centered from the neutral axis. Is it itself the value of h by 2. So we don't have to write t also here. So this was the correction. So you can write that h by 2. So we got finally the value of q equals to vbht by I. Yeah, we got this value of q. Let's have that final value of h. So final value of h equals to vbht by I into b by 2. So we got a value of vb square ht by 2I. Yeah, vb square ht by 2I. Now from that summation of moments, if you substitute that ve equals to hh, now in that equation ve equals to hh, in that equation you substitute the value of h. So we can write now v into e equals to h vb square ht by 2I into value of h. So we got that eccentricity of the shear center from the point O, that equals to b square h square t by 2I. So this is the eccentricity of that shear center from the location of O. That's b square h square t by 2I. So if you have that section, you say center to center distance is h between the flanges, and we have width of b for the flange, and you have some thickness of t for the flange. For the thickness, we have t thickness for the web also, so we have thickness of t, and we can solve for the moment of inertia for this section, I neutral axis, you can say. So we got this value. Let's have that now. Let's solve one of the problems. Let's solve one of the problems on this case. Let's solve one of the problems on this case. So you have this channel section. Thickness of 10, and width of 50, and depth of total 100. So depth is total 100. So if you say what is the and the load is passing at some eccentricity, along the principal axis. So load is passing perpendicular to the principal axis, but we can say axis of symmetry. But the point, the shear center is along the axis of symmetry. Your G is somewhere here, so your shear force is passing at some eccentricity E from the center O, and you would say, what is the location of shear center? Let's say the units of this one is your mm. Let's call them as mm. So we know the equation. Do we know the equation? That b square h square t by 2I, b square h square t by 2I, b square h square t by 2I. Now we know that b value equals to 50. You know that t value equals to 10. But what is the value of h? Can you get the value of h? I can say value of h would be the center to center between the two flanges. Let's say this is your value of h. That would be equals to h equals to 100 minus t by 2 minus t by 2. That's 100 minus 10. That's 90. So you substitute the values that we can write. B square is your 50 square. H square is your 10 square plus thickness value of t. Thickness of 90. 90 square plus thickness of 10. 90 square plus 10. 90 square into 10 divided by 2 into I. But what is the value of I? I neutral axis. What's the value of I? How can we solve this? We have two options. You can say you can make the entire rectangle you can make this as an entire rectangle. You can say I value would be equals to BD cube by 12. BD cube by 12. And you subtract the lower triangle, smaller rectangle, this part. This is having dimensions of, this is 10, this is then 40, and this is total of 100 minus 20, that's 80. So you can write minus 40 into 80 cube by 12. So that's also equals to, if you solve it by separate those separated three rectangles, you can solve in that fashion also. Let's say you have a bigger rectangle of width 10 and 100 cube by 12. Then you add those two rectangles at some distance of d from the neutral axis. So 2 times BD cube by 12. So you are left with, now you solve it for this part first. Now we have left with 40 times 40 width of 40 only. So we write 40 into 10 cube by 12, and the area into d square, plus area into d square. What is the value of d from the neutral axis? The value of d for the up to the neutral axis would be h by 2. That's 45. H by 2, that's 45 square. So you can get the direct values between, you can have the same values that are equals to 2.46 10 to the power 6 mm power 4. So you got the value of I, and you substitute here value of I. We have the units of mm power 5 by mm power 4. Finally, a unit value of 16.67 millimeter. So at this distance from the center O, you can apply the shear force, resultant shear force, that's external shear force from the shear force diagram. So on this, you can apply this at this location, and it can have no twisting, only bending. So that's why it's called as flexural center. So that means 16.67. initially this part is your 5, O to that end part, this was your 5. That means this part left with this one is your that 16.67 minus 5. Okay, let's have one more final problem for the shear stresses that we have about the shear center itself. Let's have the problem that we call that we have some member that's in the form of arc. So this is an arc member, we can say. We have it is in the form of arc of a circle such that its central axis, it's making an angle of 45, such that your from the center we are making 45 from the both sides, 45. So this is your member. So the thickness, we can say radius up to the center. The radius up to the center, I would take the radius up to the center. The radius up to the center equals to 10 centimeter. We can take radius up to the center. If the question was up to the end, we can take also that one. So radius is up to the center, or up to the center. Let's say the radius is only up to the center. And we need to say where should be the location of the shear center. Shear center should be where located? Shear center. You have to apply a load by the symmetry. We say if from the both axes we are making an angle of 45. That means this is your line of symmetry. So on that line of symmetry somewhere your shear center would be there. If you apply the load, that shear force V here, there would be no twisting. So let's say this is at some distance of E, and we know that we can apply summation of moments at any point. We can take this point as O. We can apply summation of moments at O based on this factor, because if you take moments about this point, there we have to say what you have to get this effect because of this one. That's difficult to calculate, but because we know that the distance is R and we know that theta here, some value of theta, so it would become easy if you see what's the if there is some shear flow in this one. If there is some shear flow in this one, we know that would be acting at some distance of R, and we would know its component also at some theta. So we can get the equilibrium of forces about this one, summation of moments about point O. So that means we have to take the eccentricity from this S to O as value of E. So let's say this is the eccentricity of that shear center from the center O. So we want to now finally conclude that there would be some net horizontal shear. There would be some horizontal tangential shear along the surface of that arc H, and if the resultant V is acting at a distance of E from the center, and you can say some H into some R, that equals to V into E. Can we say that? But your along the arc, your H is constant, your shear flow is constant. Your along the R, we can say along the arc, your Q value is constant. Q naught is constant, and we want to say what is the value of Q. And for the value of Q, we have the shear stress equation, that VQ by IT, and from that we can say shear flow equals to VQ by I. If you got the value of shear flow would be equals to V integral Y dA, and I we can calculate for the arc, we can say Y square dA, because we have arc, and we can calculate by this method, that integral Y dA and integral Y square dA. That's first moment of area, and this is your second moment of area. So we want to say what is the value of Y. At Y from neutral axis, you take some strip, because your theta varies along the arc, your theta is varying. You take any arc, you take any element, your theta is varying at that point. So you take some differential element of area dA, then you have first moment of area and second moment of area. Accordingly, then you can calculate the value of shear flow. Let's take that. Let's say that we have this one. We have this arc of a circle. This is your element. Let's say this is your element, and this is your neutral axis. Let's say this is your neutral axis, and this is your point O. I know that the total theta, we have maximum theta of 45. This is 45. And similarly from this side we have 45. And if I take any differential element, let's take any differential element. Let's say I take an element of area equals to dA. That equals to, I would say, let's make it in a straight line. Let's say this is the radius R. This is the radius R. Similarly, we can have radius R. Let's say this is also radius R, and this is also radius R. So you go from neutral axis. Because for the arc members we can't take in terms of y and x. We take in terms of theta. So you go to some value of theta from neutral axis. And there you take some strip. Of area, of some area dA, such that that differential element dA is making an angle of d theta at the O. So let's say this theta is d theta, and I would say the value of this is radius R, and this would be equals to the length here would be equals to r d theta. Okay, the value of the length along the surface would be r d theta. Okay, now what's the area of that dA? Let's say the thickness of the member is d. Let's say the thickness of the member is d. Let's say the thickness of the member is d. So I would write that total area of d times r d theta. So we got the value of that small differential area, d r d theta. Now we want to say we got the area. We have to calculate first moment of area and second moment of area. For that we got the value of dA. Now we need that value of y. So you go to some point A at a distance of y from the neutral axis. So there we have, that means we go to some theta from the neutral axis. There we have some point, and area above that point, if you take that differential element, I would say the value of y would be equals to by the triangle we have this triangle. So this is your r, this is your y, this is theta. Then we can say your value of y would be equals to r sine theta. So we got the value of y also. So once we got these two values, and we can say your first moment of area, that would be equals to y dA, and the limits for that particular location of A, for the particular location of that point A, we have the limits from theta to maximum. It can go to the value of your dA can go maximum value of 45. So we can say that theta to 45 degrees. So I can write theta to 45, that's pi by 4. So I go to this value, and you substitute the values of y and dA. So I have to solve then. So integral theta to pi by 4, y is your r sine theta, and value of dA equals to dr d theta. So you solve this one. So we got value of r square sine theta d theta and t times, so integral 0 theta to some pi by 4. So what is the value of sine theta d theta? So that's cos minus cos times. So we got the value of minus cos theta 0 to pi by 4 and tr square. So we got this value of that value of tr square cos theta minus cos of pi by 4. We got this value. Okay, now we got this value of, that's what we call as first moment of area. Now we need to get the second moment of area. Now second moment of area is your I neutral axis, that is integral y square dA. So about the neutral axis you have symmetry. About the neutral axis you have symmetry. If you take the first part, we know the value of I, y and a dA. So we have to take the limits. Now if you're talking about that, what should be the moment of inertia about that neutral axis? So your theta would be from 0 degrees because you're talking about the neutral axis, so your theta goes from 0 to 45, and it's for the both sides. From the both sides we have same value, so we can say that your theta goes from minus pi by 4 to pi by 4. That's also we can write 2 times 0 to pi by 4 y square dA, because your second moment of area does not take negatives, because your second moment of area is always positive, always positive. So we can take that 2 times 0 to pi by 4 y square dA. So you substitute the value of that 0 to pi by 4 r square sine square theta and tr d theta, and you have to solve this one now. So we got that tr cube 2tr cube and sine square theta d theta integral, and this part we know that is equals to 1 minus cos 2 theta by 2, and d theta you have to integral it. So we will solve only this integral part. Let's calculate this integral part. That would be equals to integral 1 by 2 of theta, that is d theta, that we can say theta, and we have one more, that is cos 2 theta by 2, that is sine 2 theta divided by 2. So limits are from 0 to pi by 4. So you got the final value of 1 by 2 that pi by 4 minus 0 minus sine 2 theta, sine of 2 into theta, minus of sine of 2 into 0 and whole divided by 2. So you got this value, we got this value. So you can solve that 1 by 2 pi by 4 minus you have this pi by 2, so that's value of 1 by 2, and this one is 0. So we got this value of 1 by 2 pi by 4 minus 1 by 2, and we have already that 2tr cube, so we can write that I equals to 2tr cube, and value of that integral equals to 1 by 2 pi by 4 minus 1 by 2. So final value of this one, I equals to this one, and now we can calculate the shear flow equation we have. So let's write that shear flow equation. Q equals to V y square y dA integral and y square dA integral, and this is your values. So we can write equals to V times your value of y dA. What's the value of y dA? Value of y dA, that's AY bar, that is this one. So tr square cos theta minus cos pi by 4. So tr square cos theta minus cos pi by 4 divided by integral y square dA, 2tr cube into some value 1 by 2 pi by 4 minus 1 by 2. So final value of Q shear flow is equals to this one. So we can simplify it. So we got a value of V, this goes, we are left with that R, we are left with the R here, so we are left with R, and this 2 goes, and we can say in terms of, can write it in terms of cos theta. So we write cos theta minus cos pi by 4, that's 1 by cos pi by 4 is your 1 by root 2, and divided by pi by 4 minus 1 by 2. So we got this value of that shear flow. We got, or this one, we can keep it in this way, or we can keep cos pi by 4 as it's. So we got this value of shear flow. But actual question was that, what was the problem we had? Actual problem was that we had that some problem. Now we say that this is your shear flow. It is a function of theta. You see that the shear flow is a function of theta. So shear flow is a function of theta. Shear flow is a function of theta. So if you want to get overall shear force, I would say shear force, this shear flow, if you multiply with the length, you would get smaller shear force. Let's say you were calculated for small d theta, your length was along the surface, that was rd theta. So if there was some shear flow for this length of rd theta, let's say the section was in this fashion. So you said that for this length of RD theta, your shear flow equals to Q. If you want to get smaller force of that length, for that length, I would say shear force per unit length. I would say shear force per unit length RD theta, that is equals to shear flow. And if I want to say what is the total force on that differential element, I would write FDX, force on that differential element, that would be equals to FDX, that is Q times RD theta. Okay, that's Q times RD theta. So for the entire force, I have to integrate it. For the entire force, I have to integrate it from the limits of that minus pi by 4 to pi by 4. So this is your 45 to 45. So I can integrate it F. I can get total force of F equals to, and that F, let's say that resultant F is somewhere here, that's acting at a distance of R from the that point O. So I would write total F equals to integral of this one and integral of this one. That's integral minus pi by 4 to pi by 4 Q R D theta. So we have to solve this one now. You put the limits, you substitute the limits of that minus pi by 4 to pi by 4. So we can write here. So your total force of F equals to that shear force of F equals to V by R cos theta minus 1 by root 2. Let's say this value pi by 4 minus 1 by 2. This is equals to some value of A. Let's solve keep it as a value of A. So we got a value of V by AR cos theta minus 1 by 2. So this is your shear flow. You have to multiply with the length RD theta. So you got a value of RD theta also, and you apply the limits minus pi by 4 to the pi by 4. So if you solve now this one, you can say this is equals to some V by A cos theta minus 1 by root 2 d theta integral. Let's use the integral. Let's calculate that. I would say cos theta d theta, that is sine theta, and the limits are from pi by 4 to minus sine of minus pi by 4, because limits are from minus pi by 4 to pi by 4. So you got this one. Similarly, you can get 1 by root 2 of theta. 1 by root 2 of theta. That value of theta would be equals to pi by 4 minus pi by 4. Okay, so you got this final value. So once you know the shear force and once you know the A, you got the value of horizontal force. This is your F. Final force of F equals to this one. And by the moments of that summation of moments about the point O, let's calculate that one. I would say, let's say there is some force F, net force of F along that curve, that's acting at a distance of R, that's acting at R from O. So I can write some value of F into R, that should be equals to, this is your clockwise, let's assume that this is clockwise, and shear force, the applied shear force on the section, that should be V times V into E. So we can write that equation, FR equals to VE. FR equals to VE. So we can solve that. FR equals to VE. So you multiply that. If you say F into R equals to V into E, so we get the value of E. So this was your F. You multiply with R. You multiply with R. You multiply with R. So this becomes your FR. That equals to V into E. So your E goes to 0. So E goes cancelled. So we got the value of E equals to R times some value of A. The value of A was equals to pi by 4 minus 1 by 2. So we got the value of A, and then the value of sine pi by 4 2 times, because this is sine of minus theta, that is minus sine theta, so it becomes positive. So finally 2 times sine pi by 4, that is 2 times 1 by root 2 minus, this is your 1 by root 2, and then 2 times pi by 4, and that's positive. So we got this value, and we want to say we know the value of R. That is equals to 10 centimeter. That's equals to 10 centimeter, and you substitute the value of R equals to 10 centimeter into some factor. Here we have this factor. So finally you calculate the value of E, that is equals to 10.0 10.6340 centimeter. 10.6340 centimeter. 10.6340 centimeter. 10.6340 centimeter. See the thing that we have already that this was your radius of R, that is equals to 10 centimeter. If you want to go 10.6340, that means if I know the thickness, let's say the thickness equals to 1 centimeter. Let's say the thickness is 1 centimeter. That means this value would be equals to 0.5 centimeter. That means net value of 10.5 would be up to this point. Then after that total E equals to 10.6340. So that means you have to go, that means this distance should be equals to 0.1340 centimeter. 0.1340 centimeter. So this is the location of the shear center from the point O. Hope you enjoyed the shear stresses. Hope you enjoyed the shear stresses in the beams, thereafter shear flow, and after that shear center. Thank you for watching this series of those strength of material by the concrete pad that delivers the things that are very important for your civil. Thank you for watching this series.